Hey there, welcome back to my YouTube channel, the School of Mathematics, a place where we talk about everything mathematics and academic. If it's your first time here, please subscribe, like, share, and comment and let us know what you think about the topic that is discussed today. So, today the video is going to be a little bit short. Uh, what I want to talk about is the distinction between pure and applied mathematics, which I think we can all agree that those are the two most spoken about, branches of mathematics. So a lot of people have a lot of questions regarding that. What is pure mathematics? What is applied mathematics? What is the difference? What do each of them, serve? What is their purpose? So that's what I'm going to touch on today. So I can start by saying that pure math and applied math, yes, they're not the same. Although somewhere, somewhat, they have the similarities, or one can overlap to the other, whereas the other one can overlap, or one can influence the other, or one apply to the other, and so forth. But in the, just to say it without going too much into detail or technicalities, basic distinction between them could be that pure math is oftentimes the mathematics that is separate from the real world or the physical world. It's mostly directed into answering questions, solving problems, and studying concepts that don't necessarily apply or have a physical application into this physical world that we're in. Whereas the applied mathematics is totally opposite. It's the mathematics that has the physical application. However, I might say this though, as much as I said pure math, it was not necessarily meant to apply in the physical world, or not necessarily it was not meant for that, but it doesn't necessarily serve the purpose of applying to the physical world. However, it does solve problems into the physical world. It answers questions that are relating to the physical world, and it actually analyzes problems and brings the solutions that contribute into the physical world. That is why today we have pure mathematics concepts that are actually used into applied mathematics. I mean, a lot of people argue that if you read back into the days, into the ancient mathematics, that pure mathematics was rather meant to, it was rather meant for people who were doing it for their own sake, not necessarily intending to solve like problems in the real world. But looking now, fast forward to recently and currently, a lot of concepts that come from pure mathematics, they actually apply into the physical world. And not only do they apply into the physical world, but they also apply into various fields like your economics, your finance, your engineering, your medicine, biology, and so forth. I mean, take number theory, for instance. Number theory, for the longest time, it is considered as the most useless majority of mathematics. But today, it is actually applied into the computer encryption system. If you do any online purchase, or if you do any online shopping, you should actually say thanks to number theory, because that whole system is modeled and structured using number theory. So that is exactly where I'm actually going with this whole topic. However, mathematics, it differs. Yes, pure math is more abstract. It's more of that, others would like to call it crazy math, the imaginary, the counterintuitive mathematics, the one that is imaginary, the one that you cannot even probably imagine. But whereas on the other hand, applied mathematics is the one that is applied, it's the one that is used into engineering. If you're studying engineering into university, you're mostly going to deal with applied mathematics. There's no need for you to deal with pure mathematics. There's no need for you to take courses like analysis, real analysis, topology, abstract algebra, because you're not going to use them anyway into engineering. Instead, you'll be dealing with things like fluid dynamics and whatever, fluid mechanics and so forth, where it's just a combination of calculus, linear algebra, and so and many mathematics majority. So, but today I want to focus particularly into pure math, and then we'll dedicate another video where we can talk broadly, and into detail about applied mathematics. So, for instance, I wanted to talk about two of the most important things in mathematics. So, in mathematics, we're dealing with facts, and concrete evidence. So, if you say something is true in math, you have to prove it. If you say something is true, you prove it. If you say it's false, then you have to support that statement with a counter example. So, for instance, pure math looks something like this, but it's going to be a little like pure math. So I want to take one of the proofs into this video today, and then let us discuss it. And because I want to show you that pure math deals with proof techniques, proving theorems, proving lemmas, and proving there's certain functions and all of that. So that is what pure math is actually based on. So I want us to look into one of the proofs, one of my favorite proofs, or rather one of the proofs that I like to, one of my go-to proofs when I'm explaining, what is it that we're proving exactly. Because a lot of people ask me, okay, you say pure math is about proofs. What is it that you're proving? I'm like, oh, no, we're proving theorems actually. What kind of theorem and what are you proving them to be? What is this proof thing? So I want us to take one proof today, one short proof that it can give an idea of exactly where is this concept of pure math structured around. So there's this proof. I'm sure some of you, if you followed mathematics, you know that it has been going around and a lot of people know it. Like proving that square root of 2 is irrational. So we have different types of proof techniques. We have proof by contradiction, we have direct proof, we have contrapositive proof. So in this case, I want to take one of the proofs because I can't take all of them because of time. But today I can give you a glimpse of what the proof technique is all about. So I'm going to talk about the proof by contradiction. So when you prove something by contradiction, you actually assume the contrary. So in this case, how do you prove this? You prove by assuming that this root of 2 is actually rational. So let's go into it. So if you assume, excuse my writing, I know I'm really bad at writing on the board, but I hope everything is clear. So assuming that root 2 is rational, it then further implies that when something is rational, it can be expressed as a form of a fraction, right? So you can say root 2 is equals to a over b. It can be represented as a over b, where b is not equals to 0 and a, b are elements of integers, right? So where a and b are elements of integers and b is not equal to 0, why is b not equal to 0? Because if b is equal to 0, then the whole thing is going to be undefined. Now, if you can manipulate this a little bit, if we square both sides, getting rid of the square root, then it's 2 equals to a squared over b squared. Here what happened, the laws of exponents. If a over b to exponent, all of them to exponent c, is a to exponent c over b to exponent c. So that's pretty much what happened here. But if we make a squared the subject of the formula here, then we're going to come across a squared equals to 2b squared. And if we have something like this of an a that is represented as 2 times something, as we have already stated here that b and a are elements of integers, which then implies that a squared is even, because any number, any letter here that is representing an integer, if you multiply it by 2, whatever number that you're going to, whatever integer you're going to substitute here is going to give you an even number. 2 times 2 is 4. 2 times 4 is 8, and so forth. So that is what it means to be an even number. Now, if a squared is even, of course a is even. Why? Because you know that even number is a product of 2 even numbers. So if even times even equals to even. So if even times even equals to even, and a squared obviously is a result of a times a, which is a squared, and a squared is even, which means a is also even, because for a squared to be even, because A is a product of two A's multiplied together. It means A is also even. So I hope we agree on that one. Now, let me remove this so that we can continue with our proof. So, this will then imply that A is also even, right? But if A is even, it means it can be represented as 2 times whatever, if whatever is also an element of integer. So, it means, it implies that A can be represented as 2, let's use K in this case, right? K, where K is the element of integers, right? But if we have A as 2K, we can easily substitute it here, right? Because we already have A squared, so let us substitute our 2K into the A squared and see what we'll get. Now, 2K squared equals to 2B squared, right? So when you open this bracket, it will be 4K squared equals to 2B squared, which then means that B squared equals to 2K squared. As you can see, if B squared can represent F2K squared, it then also implies that it means B is also even, right? Which implies that B squared is even, which also implies that B is even, right? Now, if B squared is even, which then means B is even, then it means also B can be represented as 2, but we use K, let's use T in this case, right? As 2 times T, where T is an element of integers. By the way, there's something I didn't actually mention, which is very important. For this to be rational, it will be rational under the conditions that A and B are co-prime, right? Are co-prime, meaning they cannot have any common factor other than 1. That is very important. So I didn't write it here because of the space, but I was actually planning to mention it later, like in this case. So for this to be rational, not irrational, rational, these two terms, A and B, as much as they are elements of integers, they have to also be co-prime, meaning they don't necessarily have to have any other factor than 1. I hope we agree on that one. So you put that note on the side and always be aware of that. Therefore, if we have B as 2t and we have A as 2k, let us go back into our let me do this. Let us go back into our square root of 2 is equals to A over B. Now that we have A and B, we can just substitute. A is 2k, B is 2t. But you see now, I have just given you a disclaimer that for this to be rational, it means that A and B has to be co-prime, right? Then, being co-prime means they don't have to have any other factor that they have in common other than 1. But if you can see here, they have a common factor of 2. You can actually factor out 2, which then contradicts our conditions. So if this can have a factor in common other than 1, which is 2, then it means it contradicts with our condition of co-primeness, which then it means that there's no way this can be rational, which makes it irrational. So that is how we prove that square root of 2 is irrational. By assuming first that it's rational and try to prove that it's actually rational, but somewhere in our proof, like here, as you see, is going to contradict with the rules of mathematics. And then it's going to actually show you that it cannot be rational, which then implies by default that it's actually irrational. So that is one of the proof techniques that I wanted to show you guys. But this is just the surface level of proofs. There's actually more deep and more abstract and more crazy, proofs that we can actually go into, even especially when you go into courses like topology. Now that is the highest level, a higher level of mathematics, of the abstract mathematics, the math without numbers. That's what most pure mathematicians will tell you about the pure math. So yes guys, that is all for today's video. Remember, we're just discussing the difference between pure and applied mathematics, but I wanted to lean more onto the pure mathematics concept than applied mathematics. But next time, we will tackle the applied mathematics. We will find a fun, thing to do. I don't know, there's no proof techniques in applied mathematics, but we'll find something interesting that is regarding applied mathematics, and then we will unpack it here on the video, and then we will discuss it, and then we'll keep on talking more about the pure and applied math depending on what you guys want to hear more. Let me know what you think on the comment section. Comment with a question if you have a question, comment with a suggestion, comment with whatever that is it that you want to learn more or rather hear about. But anyway, for me guys, that's all for today.